Hello, everyone, and welcome. Today, we're diving into a fundamental topic in algebra, the laws of exponents. We'll be covering the core rules that govern how we work with powers. By the end of this lesson, you will be able to, first, understand and apply the basic laws of exponents. Second, use these laws to simplify expressions, including those with negative and zero exponents. And third, use these skills to solve equations where the unknown is in the exponent. Let's get started by defining our terms. In an expression like a to the power of n, we call a the base, and n is the exponent, which you might also hear called the power or the index. The exponent tells us how many times to multiply the base by itself. Now let's look at our first key rule, the multiplication rule. It states that when you multiply two powers with the same base, you add their exponents. Let's see why this works with a simple example. Consider 2 cubed times 2 squared. 2 cubed is just 2 times 2 times 2, and 2 squared is 2 times 2. Altogether, we are multiplying 5 2's, which is 2 to the power of 5. Notice that 5 is simply 3 plus 2. So when we multiply powers with the same base, we add the exponents. Let's apply this to a worked example. Let's simplify x to the 6th times x to the 3rd. Here the base is x, and we are multiplying, so we add the exponents 6 plus 3. This gives us our simplified answer, x to the power of 9. Now for our second rule, which deals with division. The division rule. When you divide two powers with the same base, you subtract the exponents. Again, let's look at an example to understand why. If we have y to the 5th divided by y squared, we can write it out. We can cancel 2 of the y's from the top and bottom, leaving us with 3 y's in the numerator, or y cubed. Notice that 3 is 5 minus 2. So when dividing powers with the same base, we subtract the exponent of the denominator from the exponent of the numerator. Let's try this with another example. Simplify y to the 8th divided by y squared. Since we are dividing and the bases are the same, we subtract the exponents. 8 minus 2 gives us 6. The result is y to the power of 6. The third fundamental rule is the power of a power rule. This rule says that when you raise a power to another power, you multiply the exponents. For instance, a squared cubed means we multiply a squared by itself 3 times. Using our multiplication rule, we add the exponents. 2 plus 2 plus 2, which is 6. Notice that 6 is the same as 2 times 3. So raising a power to a power means we multiply the exponents. Let's simplify 7 cubed, all raised to the power of 5. Here we have a power raised to another power, so we multiply the exponents. 3 times 5 is 15. The simplified form is 7 to the power of 15. We don't need to calculate the final number. Now let's use these rules to explore some special cases, starting with the zero exponent. What does it mean to raise a number to the power of 0? We can figure this out using the division rule we just learned. Let's look at a power divided by itself, say a to the m over a to the m. According to our division rule, we subtract the exponents, which gives us a to the power of m minus m, or a to the power of 0. But we also know from basic arithmetic that any non-zero number divided by itself is 1. Since both expressions are equal to a to the m over a to the m, they must be equal to each other. Therefore, a to the power of 0 equals 1 for any non-zero base a. This is a very important identity to remember. Any non-zero base raised to the 0 power is 1. Now what about negative exponents? A negative exponent indicates a reciprocal. Let's see where this comes from. Again, using the division rule, let's consider a to the 0 divided by a to the n. Using the division rule, this is a to the power of 0 minus n, which is a to the negative n. But we just established that a to the 0 is 1, so a to the 0 over a to the n is the same as 1 over a to the n. By equating the two results, we find that a to the negative n is equal to 1 over a to the n. A negative exponent simply means to move the power from the numerator to the denominator, or vice versa, and make the exponent positive. Let's see this in action. Let's write 2 to the negative 4 as a fraction. Using our rule, 2 to the negative 4 is the same as 1 over 2 to the positive 4. 2 to the 4th is 16, so the answer is 1/16. Here's a slightly trickier one. Be careful about what the exponent applies to. Let's write 4x to the negative 3 as a fraction. A common mistake here is to apply the exponent to the 4 as well. But there are no parentheses, so the negative 3 exponent only applies to its immediate base, which is x. So the 4 stays in the numerator, and x to the negative 3 becomes 1 over x cubed. Multiplying them gives us 4 over x cubed. All right, let's start combining these rules and work with expressions that have coefficients. When an expression has both numbers and algebraic variables, we can handle them separately. This works because multiplication is commutative and associative, meaning we can reorder and regroup the terms. Let's simplify 2b cubed times 7b to the fourth. First, let's reorder the multiplication to group the numbers together and the variables together. So we have 2 times 7 and b cubed times b to the fourth. 2 times 7 is 14. For the variables, we have the same base b, so we add the exponents, 3 plus 4. This gives us a final answer of 14b to the seventh. So you see, we just multiply the coefficients and then apply the exponent rules to the variables. The same idea applies to division. Let's simplify 6c to the ninth divided by 2c to the fourth. We can think of this as two separate fractions, the fraction with the numbers and the fraction with the variables. So we have 6 divided by 2 times c to the ninth divided by c to the fourth. 6 divided by 2 is 3. For the variables, we have the same base c, so we subtract the exponents, 9 minus 4. This simplifies to 3c to the fifth. Again, we handle the coefficients and the variables separately. Now, let's introduce two more essential rules that deal with powers of products and powers of fractions. First, the power of a product rule. This says that if you have a product raised to a power, you can apply that power to each factor in the product. Let's see why this is true. If we take the product AB and cube it, that means we multiply AB by itself 3 times. Since we can reorder multiplication, we can group the A's together and the B's together. This gives us A cubed times B cubed. So the exponent distributes to each factor. Let's apply this to a more complex example. Let's simplify the expression 2x squared y to the negative 4, all raised to the power of 5. Here, we have a product of 3 factors inside the parentheses, 2x squared and y to the negative 4. The power of 5 applies to each of them. 2 to the fifth is 32. For the variables, we use the power of a power rule, which means we multiply the exponents. So we have x to the power of 2 times 5 and y to the power of negative 4 times 5. This gives us our final simplified expression, 32x to the 10th y to the negative 20th. We can leave the answer with a negative exponent unless asked otherwise. Next up is the power of a fraction rule. Similar to the product rule, if you have a fraction raised to a power, you can apply that power to both the numerator and the denominator. Let's tackle a challenging example that combines several of our rules. We need to simplify 2u over 3v squared, all raised to the power of negative 3. I'll show you 2 ways to do this. The first is by direct application of the rules. First, we apply the power of negative 3 to the numerator and the denominator. Then we apply the power to each factor inside. This gives us 2 to the minus 3 times u to the minus 3 in the numerator, and 3 to the minus 3 times v to the minus 6 in the denominator. To get rid of the negative exponents, we move each term with a negative exponent to the other side of the fraction bar and make its exponent positive. So 3 to the minus 3 and v to the minus 6 move to the top, and 2 to the minus 3 and u to the minus 3 move to the bottom. Finally, we evaluate the numbers. 3 cubed is 27 and 2 cubed is 8. Our final answer is 27v to the 6th over 8u cubed. Now for a second, often easier method. Remember that a negative exponent means taking the reciprocal. For a fraction, the reciprocal is found by flipping it. So we can flip the fraction inside the parentheses and change the exponent from negative 3 to positive 3. Now we just apply the positive exponent of 3 to the numerator and denominator and simplify. We get the exact same answer, but often with fewer steps and less chance for error. This is a very useful trick to remember. Let's look at another type of simplification problem. What happens when we have addition or subtraction in the numerator of a fraction? Consider this expression, 16a to the 5th b squared minus 12, ab to the 4th, all divided by 4ab squared. A common mistake is to try to cancel terms incorrectly. The key here is that the denominator divides the entire numerator. We can split this into 2 separate fractions, with each term from the numerator divided by the denominator. This is because division distributes over addition and subtraction. Now we have two simpler problems that we know how to solve. For the first term, 16 divided by 4 is 4. A to the fifth divided by a is a to the fourth. And b squared divided by b squared is b to the 0, which is just 1. So the first term simplifies to 4a to the fourth. For the second term, 12 divided by 4 is 3. A divided by a to the 0, or 1, and b to the fourth divided by b squared is b squared. So the second term simplifies to 3b squared. Putting it all back together, our final simplified expression is 4a to the fourth minus 3b squared. Remember to split the fraction first when you have a sum or difference on top. Now we're going to use these laws to solve a new type of problem, exponential equations. These are equations where the variable we need to solve for, like x, is in the exponent. The core principle for solving these is very straightforward. If you can write an equation so that you have the same base on both sides, then the exponents must be equal. This is the key to solving these problems. So our strategy will always be to rewrite the numbers in the equation so they share a common base. Let's warm up with an expression first. Let's express 3 to the fourth times 9 to the fifth as a single power of 3. The bases are not the same, so we can't apply our rule directly. But we can see that 9 can be written as a power of 3. 9 is 3 squared. We substitute 3 squared for 9. Now we have a power to a power, so we multiply the exponents to get 3 to the 10th. Finally, we are multiplying powers with the same base, so we add the exponents 4 plus 10 to get 3 to the 14th. So k is 14. Now let's use this strategy to solve an equation. Let's solve 2 to the power of x plus 6 equals 8 to the power of x. Again, the bases are different. We need to find a common base. The left side has base 2, and we can write 8 as a power of 2. 8 is 2 cubed. We substitute 2 cubed for 8. On the right side, we have a power to a power, so we multiply the exponents to get 2 to the power of 3x. Now we have the same base, 2, on both sides. This means the exponents must be equal, so x plus 6 must equal 3x. Solving this simple linear equation, we subtract x from both sides to get 6 equals 2x, and then divide by 2 to find that x equals 3. Let's try one more that involves a fraction. Let's solve 3 to the power of 2x plus 5 equals 1 over 27. Our common base is clearly 3. We know that 27 is 3 cubed. Therefore, 1 over 27 is 1 over 3 cubed, which we can write using a negative exponent as 3 to the negative 3. Now our equation is 3 to the 2x plus 5 equals 3 to the negative 3. The bases are the same, so we set the exponents equal. 2x plus 5 equals negative 3. Subtracting 5 from both sides gives 2x equals negative 8, and dividing by 2 gives our final answer, x equals negative 4. To wrap up, let's see how these laws of exponents can be applied to model real-life situations. We have a model for a baby fish. Its length, L, in centimeters is given in terms of its age, T, in days, and its mass, M, in grams, is given in terms of its length. The length is L equals 2t squared, and the mass is M equals 4L cubed. Part A asks us to find an expression for the mass M, directly in terms of the age T. To do this, we need to combine the two equations. We can substitute the expression for L, which is 2t squared, into the equation for M. This gives us M equals 4 times the quantity 2t squared cubed. Now we simplify using our exponent laws. We apply the power of 3 to both the 2 and the t squared. 2 cubed is 8, and t squared cubed is t to the 6th. Multiplying by the 4 outside gives us our final model, m equals 32t to the 6th. Part B asks for the age of the fish when its mass is 1,000 grams. We'll use the equation we just derived. We set m equal to 1,000. To solve for t, we first isolate t to the 6th by dividing both sides by 32. 1,000 divided by 32 is 31.25. To find t, we need to undo the power of 6. We do this by taking the 6th root of both sides. The 6th root of 31.25 is approximately 1.77. So the fish reaches a mass of 1,000 grams in just under 2 days, according to this model. Finally, Part C asks us to think critically about the model. It asks why the model is unlikely to be accurate for a long time, say after 100 days. The equation m equals 32t to the 6th is a power function that increases very rapidly. It suggests the fish's mass will grow indefinitely and at an ever-increasing rate. In reality, A fish's growth slows down as it gets older and approaches a maximum size. So, this model is probably only good for a very short period when the fish is very young. It's a good reminder that mathematical models are often simplifications of reality and have limitations. All right, let's quickly recap what we've learned today. We've covered the 7 key laws of exponents. When multiplying powers with the same base, you add the exponents. When dividing, you subtract. When raising a power to a power, you multiply. An exponent distributes over products and fractions. Any non-zero base to the power of 0 is 1. And a negative exponent means taking the reciprocal. We saw how to use these rules to simplify a wide variety of expressions, from simple products to complex fractions. We also learned a powerful technique for solving exponential equations. Find a common base and equate the exponents. Looking back at our objectives, we have now covered how to understand and apply these laws, how to simplify expressions, and how to solve exponential equations. These skills are foundational for many other topics in mathematics, including logarithms, which we'll be covering soon. Make sure to practice these concepts with the exercises in your textbook. The more you use these rules, the more intuitive they will become. That's all for today. Thank you.